All right, welcome back to our unit here on gases. Today's topic is Boyle's and Charles' law. Lesson 2 of 3, your objectives are as follows. To become familiar with units of temperature and pressure, to understand the inversely proportional relationship that exists for Boyle's law, and to understand the proportional relationship of Charles' law, and finally to understand how we use Charles' law to calculate absolute zero. So, Quickwrite. What do you think would happen to the size of a balloon if it was brought from sea level up to Lake Tahoe? What do you think happens to the volume of a car's tire on a hot summer day? How do you think heat affects the pressure inside of the tire? In terms of heat and energy, what do you think a temperature of absolute zero means? Okay, and what do you think would happen to a soda can if all the air inside the can was removed? Okay, go ahead and pause that while you do your quick write. I'm going to move on. Okay, so units of temperature and pressure at STP. Earlier we discussed the molar volume of a gas, which at STP is equal to 273 Kelvin or 0 degrees Celsius, and a pressure of 1 atmosphere. And the volume of the gas at these conditions was 22.4 liters. Okay. Well, other units of temperature and pressure exist. So we're going to look at pressures and temperature outside of these. Okay, so STP is a set of conditions, if you recall, okay, from our last lesson, that exist at 1 atmosphere, okay, ATM of pressure, and a temperature of 273 Kelvin or 0 degrees Celsius. So another unit of temperature we are going to become better familiar with is the Kelvin scale. Okay, on the Kelvin scale, 0 is the absolute coldest, okay, temperature possible in our universe. Okay, nothing is colder than 0 Kelvin. It uses no negative numbers. Recall that water freezes at 0 degrees Celsius, but on the Kelvin scale, water freezes at 273 Kelvin, or 273 K. So 0 degrees Celsius is equal to 273 Kelvin. Well, one of the first units of pressure ever invented and still used today is the torr. In this case, 1 atmosphere of pressure, okay, is equal to 760 torr, or 760 millimeters of mercury. Think of torr and millimeters of mercury as the same thing. Okay, so 1 atmosphere is equal to 760 torr, or millimeters of mercury. A unit of pressure you may be familiar with is pounds per square inch. Pounds per square inch are used to measure tire pressure, like in your cars and bicycle tires. So just look on the side of your tires of your bike or your car. You'll see your tire pressure is measured in pounds per square inch. One of the few times we will actually use something other than the metric system in this class. So in this case, 1 atmosphere is equal to 14 pounds per square inch. Okay, so what are the different units of temperature and pressure at STP for your notes? Question on the left-hand side. Okay, everything under the question goes on the right-hand side of your notes. Go ahead and pause this. Okay, I'm going to move on. All right, so practice here. Convert 293 Kelvin into degrees Celsius using the following equation. Okay, and try to convert air pressures from torr, okay, into ATM. Okay, so you're just doing some unit conversions here. Go ahead and pause this while you work on this. When you're ready to check your work, hit play. Okay, so notice this equation here. Degrees Celsius plus 273 is equal to degrees Kelvin. So we're given degrees Kelvin here. Just substitute our value into our equation. Okay, solve for degrees Celsius. And we get, okay, 293 Kelvin is equal to 20 degrees Celsius. Okay, so 293 on the Kelvin scale is equal to 20 degrees Celsius here. All right, air pressure. The air pressure outside today is 960 torr. Convert this into standard atmospheres of pressure. Okay, so little dimensional analysis. Start with what the question gives us, right? And here's our conversion factor. So 760 torr in 1 atmosphere of pressure. Okay, our units cancel. and we get 1.2 atmospheres. Okay, hopefully you got that right. Okay, so Boyle's law. Boyle's law states the volume of a given sample of gas at a constant temperature changes inversely with the pressure. So volume changes inversely with the pressure. In other words, okay, if pressure goes up, volume goes down, or vice versa. It is represented by the following equation. P1 multiplied by V1 is equal to P2 multiplied by V2. Notice how the volume of a gas decreases as pressure is increased on this graph below here. Okay, so we're going to add more pressure or weight here of this gas because gases are compressible. Okay, so 1 atmosphere of pressure. Okay, now we have a volume of 400 milliliters. Add another atmosphere of pressure. Okay, now we have a volume of 200 milliliters with 2 atmospheres. Okay, 3 atmospheres of pressure. Okay, and our volume has decreased even further. Okay, so notice as pressure increased, volume here decreased. All right, and our graph shows this. Okay, so for your notes, what is Boyle's law? Question on the left-hand side, answer on the right-hand side. Go ahead and pause this, please, while you work on this. I'm going to move on. Okay, so Boyle's law problem here. A balloon at sea level has a volume of 5 liters and is at a pressure of 1 atmosphere. If this balloon is brought up to Mount Everest, where the air pressure is 0.39 atmospheres, what will be the balloon's new volume at the top of Mount Everest? Okay, so here's our initial conditions, final conditions. Think about what's given here. Okay, P1, well, the initial conditions, the balloon's at 1 atmosphere, and it has a volume of 5 liters. Okay, then we bring it up to a new pressure, where the air pressure is 0.39 atmospheres. What will be the new volume? Okay, so let's rearrange the equation for V2. We get, okay, the following equation. And let's substitute our values in. Okay, we got 1 atmosphere of pressure. Okay, a volume of 5 liters. And a pressure of 0.39 atmosphere gives us, okay, 12.8 liters. Okay, now it's your turn. Go ahead and practice here. Go ahead and pause this while you work on this. When you're ready to check your work, hit play. All right, let's see how you did. So the initial conditions, we got 1 atmosphere of pressure and a balloon with 3 liters in it. Then we're brought up to Lake Tahoe where the air pressure is less. What is the new volume of the balloon? Okay. Once again, let's rearrange our equation here for V2. And now we can just substitute our initial and final conditions into our equation. 1 atmosphere times 3 liters divided by 0.65. Okay, gives us a volume of 4.6 liters. Hopefully you got that right. Okay, so Charles's law. Charles's law is pretty interesting. It states that the volume of a given sample of gas at a constant pressure is directly proportional to the temperature in kelvins. In other words, okay, the volume goes up if temperature goes up, and vice versa. If temperature goes up, volume goes up, and if temperature goes down, well, volume goes down. So it's given by the following equation. So let's add some heat to our gas here sample and see how volume changes. So we're going to add 100. We're going to heat our gas up to 100 Kelvin. Notice the volume went up to, okay, 100. Let's add even more heat now. What do you think is going to happen to our volume? We heat it up even more to 200 K or Kelvin. Okay, the volume gets bigger. And if we add even more heat, okay, we have a volume of 300 milliliters. So notice, as we add more heat, the volume increased. So for your notes, what is Charles's law? Question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write this. I'm going to move on. All right, so here's an example of a Charles' Law problem. A container of gas has a volume of 5 liters, and it's at a temperature of 100 Kelvin, or K. And then we heat up, okay, the gas to a temperature of 273 Kelvin. What is the new volume of the gas? All right, so over here we have our initial conditions and our final conditions. So the initial volume of the gas was 5 liters, all right, and it was at a temperature of 100 Kelvin. Then we heated it up to 273 Kelvin. Okay, we're trying to solve for its final volume here. So let's rearrange the equation for V2. We get, okay, V2 is equal to V1 times T2 divided by T1. Plugging in our values, we get, okay, our initial temperature, 100K, our initial volume was 5 liters, okay, and then we heated it up to 273 Kelvin. Now we can solve for, okay, now that we've isolated V2 here, we can solve for the final volume. And we get 13.65 liters. Okay, so that makes sense. We heat up a gas, its volume should increase based on Charles's law. All right, now it's your turn. Practice here, this Charles's law, okay, problem. Go ahead and pause this while you work on this. When you're ready to check your work, hit play. All right, let's see how you did. So let's plug in, once again, our initial conditions. Okay, the volume of the gas was 3 liters. It's at 195 Kelvin. All right, then we heated it up to 310 Kelvin. And now we're trying to solve for its new volume, its final volume, after it's been heated up. Okay, all right, so let's rearrange the equation and isolate V2 here. Now we can simply just plug our values into our equation, solve for V2. Okay, our initial temperature, 195 Kelvin. Our initial volume was 3 liters. And we heated it up to 310 Kelvin. Okay. And now we can solve for V2, which gives us 4.77 liters. Okay, which makes sense. Once again, okay, increasing temperature, all right, should cause the volume of the gas to get larger or increase. All right. All right, so Charles's law and absolute zero. Using Charles's law, scientists have discovered a thing called absolute zero. So the solid lines here are based on 3 different gases and how they behave as we cool them or temperature is decreased. Okay. Well, where the lines are dashed, these gases eventually liquefy or condensate, right? They go from a gas to a liquid. When we extend all of the lines, or we call this extrapolate, to 0 here, to 0 volume, an interesting thing happens, okay? So if we extrapolate, we simply just extend this line, right? We notice that they all cross at 0. Okay, well, Lord Kelvin, a scientist, noticed this, and he called this absolute zero. Okay, so like I said, they all intersect at 0 Kelvin. This suggests that negative 273 degrees Celsius, which we now call absolute zero or 0 Kelvin, is the lowest possible temperature in our universe. Nothing can be colder than that. In fact, experiments have shown that all matter cannot be cooled below this temperature. This temperature is defined as absolute zero. Like I said, a scientist by the name of Lord Kelvin recognized this and devised a whole temperature scale based on absolute zero. That is the Kelvin scale. Okay? On the Kelvin scale, okay, 0 is the lowest possible temperature, and all matter, gases, have no movement or kinetic energy. Okay, so for your notes, what is absolute zero? Okay, question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. Okay, I'm going to move on. Okay, so summarize, please. Okay, remember, you can always write your own. All right, so go ahead and complete your summary for 20 points, and we'll see you next time.